Hey guys, Miss Carlson here again. We're going to talk today about universal forces that's covered in section 4 of chapter 12. It is the last section of chapter 12 we're going to talk about. Make sure you have a good Cornell note-taking template or a notebook sheet of paper to get started on your notes. And we're going to go ahead and jump right in. And the observations of our planets, stars, and galaxies strongly suggest that there are 4 universal forces that exist throughout the universe. We've touched on some of these forces already throughout the chapters we have been working on, but we haven't really pointed them out or talked about them in much detail. They are electromagnetic forces, strong nuclear and weak nuclear, which were actually spoken about when we talked about atoms, and then gravitational, which is what we're really focusing on right now. So all of these forces act over a distance between particles of matter. They don't need to be in contact with each other, and the force is affected by the distance between those particles and basically is a measure of their strength. Now we're going to talk about each one of them individually, starting off with electromagnetic forces. Judging by the name, we are talking about electric and magnetic forces. They're very similar. They're both associated with charged particles. Electric forces are charged objects or particles. They attract each other if they're opposite and repel if they're alike. And this we normally talk about when we're discussing subatomic particles like protons and electrons of the atom. Magnetic forces would be involved with certain metals and other objects, or like magnets, of course. They have 2 poles, north and south, which also attract if they're opposite and repel if they're alike. Now, this force in particular is unique because it can both attract and repel. The other forces are not able to do that. They're more strictly attracting forces. Now, the nuclear forces we're going to talk about are the strong nuclear force, which I abbreviate S and F. It can overcome the electric force of repulsion that acts among the protons in the nucleus, which helps keep that nucleus together. And the weak nuclear force is involved in certain types of radioactive processes that we will talk about later on, actually in the last unit of our semester. I do want to briefly mention a few details about the strong nuclear force, though. It is a powerful force of attraction. It acts only on the neutrons and protons in the nucleus. It does act over short distances, though, approximately the diameter of a proton, which is 10 to the negative 15 meters long, which is very, very tiny, of course. And it is 100 times stronger than the electric force of repulsion at that distance. Now, the weak nuclear force, the only thing I'm going to say is it is an attractive force. It does only act over short ranges of 10 to the, and this should be to the negative 18 power meters. So again, still very small. Now, take a closer look at this picture. It's kind of fuzzy, but you can see that we have protons and neutrons in the nucleus. Obviously, protons are a like charged particle, so you would expect them to repel. But the strong nuclear force is what's keeping them together and stable in the nucleus of an atom. Now, gravitational forces depend heavily upon mass and distance, and it is an attractive force that acts between any 2 masses. The force, or the strength of the force, is proportional to the mass between the 2 objects. It also decreases with the squared distance between the objects, or in other words, the further something gets away from another object, the gravitational force will decrease. It is the weakest universal force, but is the most effective over long distances. And you can see in this diagram here, they're showing you 3 different scenarios, A, B, and C. A has 2 objects of the same mass, and they are attracted to each other relatively equally, designated by these arrows. It's the gravitational force of X is the blue arrow, and the gravitational force of Y is the red. Now, if you increase the mass, you're going to increase the gravitational force between those 2 objects. However, though, if you increase the distance, as in shown in scenario C, you're going to decrease the force of gravity, as shown by the magnitude of those arrows. Now, there is also something that happens with the Earth and the Moon because of their attraction to each other, and we know them as ocean tides. So the moon's inertia acts to move it away from the Earth. However, the Earth's gravitational attraction creates nearly a circular orbit of the moon around the Earth, and we call this centripetal force. The technical definition of a centripetal force is a center-directed force that continuously changes the direction of an object to make it move in a circle, which is what the moon does around the Earth. Now, this is a picture of what we're talking about. The moon does want to move away, but because of the gravitational pull of the Earth, you have this constant centripetal or circular motion that occurs with the moon moving around the Earth. And this causes an effect, or two bulges in the Earth's oceans, which again, like I said, we call tides. The side of the Earth that's closest to the moon will result in a pull, and the side farthest from the moon will also result in a pull. And the Earth's rotation creates 2 high tides and 2 low tides per day because of this pull between the two objects. And we can take a closer look. There are 2 types of tides. We have spring tides, and they occur, let me show you, when the moon and the sun are parallel to each other, so they're in a straight line. And a neap tide would then occur when the moon and the sun are perpendicular to each other. And you can see how this happens twice, depending on where the moon is. And it also happens twice with the spring tide if the moon is in between the sun and the Earth, or outside the Earth but still in line with both of them. Now, satellites are something that we use the gravitational forces as a benefit for us. And artificial satellites need only their inertia and centripetal force to keep them in space. And this is a picture of an artificial satellite right here. Low orbiting satellites are slowed by the friction of the Earth's atmosphere and will eventually re-enter Earth's atmosphere at some point. Now, the purpose of satellites, or some of its uses, there are hundreds of artificial satellites that orbit, and they can monitor Earth's weather, create detailed radar maps of the Earth's surface, obviously used again to help with weather services, using telescopes to study space, study the climate of the Earth, receive and transmit radio and microwave signals, and they can also be used to receive and transmit electromagnetic waves over great distances. And that is all we're going to talk about today. And make sure you go back and pause and play as needed, and have these notes done and completed for turn-in on Thursday. I'll see you next time.